Refraction and total internal reflection. So the first question is on refraction. A light ray travels through an air-fused quartz interface at an angle of 30 degrees to the normal. Find the speed of light in the quartz and the angle of refraction. So before we start, just a couple notes. Refraction refers to the change in the direction of a wave at a boundary where it passes from one medium into another, as a result of different wave speeds in different media. Some important terms include Snell's law. Snell's law relates the angle of incidence and angle of refraction to the wave speeds in the respective media. The index of refraction of a medium is defined as the ratio of the speed of light in vacuum to its speed in that medium. By referring to the table on page 757 in our textbook, we can find the N for the fused quartz and the air. We can see that the fused quartz, which is N2, is equal to 1.46, and the N1 for air is equal to 1.00. We're also given that the angle 1 is equal to 30 degrees. Now, from N equals C over V, we have that the velocity is equal to C over N2. When we plug in our values, we get 3 times 10 to the 8th meters per second over 1.46, and we end up getting 2.04 times 10 to the 8th meters per second. Now to find the angle. We can use Snell's law, and we have that sine theta equals N1 sine theta 1 over N2. When we plug in our values, we get 1 times sine 30 over 1.46, which gives us 0.342. So our theta 2 is equal to sine inverse of 0.342, which gives us 20 degrees. Our second question deals with total internal reflection. A diver is 1.5 meters beneath the surface of a still pond of water. At what angle must the diver shine a beam of light towards the surface in order for a person on a distant bank to see it? Before we begin, some notes on total internal reflection. Some important terms include critical angle and total internal reflection. When a ray goes from a medium of greater index of refraction to a medium of lesser index of refraction, the theta 1 will be less than theta 2, according to Snell's law. When theta 1 increases, theta 2 will also increase, but it will always be greater than theta 1. Therefore, at a certain critical angle of incidence, the angle of refraction will be 90 degrees and the refracted ray is along the media boundary. For any angle of incidence, theta 1 is greater than the critical angle, total internal reflection occurs and the surface acts like a mirror. Now, by referring to the table on page 757 in the textbook, we can see that our N1 for the water is equal to 1.33 and our N2 for air is equal to 1.00. And we're given that our theta 2 angle is equal to 90 degrees. When the refracted light is along the boundary, the angle in water is equal to the critical angle. So our angle 1 is equal to the critical angle, which is equal to sine inverse of N2 over N1. When we plug in our values, we get sine inverse of 1 over 1.33, which gives us sine inverse of 0.752, or 49 degrees. We can also use Snell's law, as in the picture at the bottom. Sine theta 1 is equal to N2 sine theta 2 over N1. When we plug in our values, we get 1 times sine 90 over 1.33, which gives us 0.752. Therefore, our theta 1 is equal to sine inverse of 0.752, and we get 49 degrees. Thank you.